October 1945. Building 26, Raytheon Manufacturing Company, Waltham, Massachusetts. Percy Spencer stood 3 feet from an active magnetron, the British-designed vacuum tube that generated microwave radiation for military radar systems. He was 51 years old. Self-educated, no formal engineering degree. He had risen from poverty in Maine to become Raytheon's most prolific innovator, holder of 120 patents. The war had just ended. Raytheon employed 9,000 workers building magnetrons for the military. With peace, that contract would disappear. Spencer spent his days solving production problems on the magnetron assembly line. The tubes operated at 2,450 MHz, generating electromagnetic waves roughly 12 centimeters long. Britain's Randall and Boot had invented the cavity magnetron in 1940. It gave Allied radar a decisive advantage. Detection range increased dramatically. German submarines could be tracked from aircraft. The Battle of Britain turned partly on this technology. The magnetron itself was a copper cylinder about the size of a hockey puck. Inside, electrons spiraled through a magnetic field, releasing microwave energy. The device grew hot during operation. Engineers understood this as waste heat, energy lost to inefficiency. Spencer carried a chocolate bar in his shirt pocket that afternoon. He didn't plan to eat it immediately. Just something he'd grabbed from his desk. The factory floor ran warm from machinery and autumn sun through tall windows. He stood near the magnetron for several minutes, discussing voltage regulation with a technician. When he reached for the chocolate bar, he found it melted. Not softened. Melted. Completely liquefied inside the wrapper. The fabric of his shirt remained merely warm. The chocolate had heated from the inside. Spencer looked at the magnetron. Back at the chocolate. The distance between them. The insulation of the wrapper and his shirt. Heat didn't work this way. Radiant heat warmed surfaces first, then penetrated inward. This was different. He called over his assistant. "Bring me some popcorn kernels." The next day, Spencer placed unpopped corn kernels in a paper bag near the active magnetron. The kernels began popping within seconds. Violently. Several shot out of the bag. Other engineers gathered. They'd never seen popcorn cook this quickly. No hot oil. No direct heat source. Just proximity to the magnetron. Spencer's mind moved to the mechanism. Microwave radiation at 2,450 MHz. Water molecules vibrating. Friction generating heat from molecular motion. Food heated from within rather than from surface contact. This wasn't waste heat. This was a cooking method. Spencer spent the next week conducting systematic experiments. He brought various foods into Building 26. Eggs. Bread. Meat. Vegetables. Each responded differently to the microwave field. Eggs exploded from rapid internal pressure. Bread dried before browning. Meat cooked unevenly. But everything heated faster than conventional methods. The principle was sound. The application needed refinement. He constructed a metal box to contain the radiation and focus the energy. The enclosure measured roughly 1 cubic foot. He cut a hole for the magnetron. The confined space concentrated the microwaves. Heating efficiency improved dramatically. By November 1945, Spencer had built a prototype cooking device. It wasn't elegant. Metal box. Industrial magnetron. Crude door mechanism. But it cooked food using microwave radiation in a controlled environment. He heated a cup of water to boiling in under 2 minutes. A conventional electric hot plate required 8 minutes. Raytheon executives saw the commercial potential immediately. The military magnetron contract was ending. The company needed new markets. A cooking device using radar technology could fill that gap. They filed the patent application on October 8, 1945. Just 3 months after Spencer's chocolate melted. January 1946. Raytheon's research division, Waltham. Engineers gathered around Spencer's prototype, now designated Project R1. The question wasn't whether microwaves could cook food. Spencer had proven that. The question was whether anyone would buy a microwave oven. The prototype stood 6 feet tall and weighed 750 pounds. The magnetron required water cooling. Power consumption reached 3,000 watts. Installation required dedicated 220-volt electrical service. The device cost roughly $5,000 to build, equivalent to $75,000 in 2025 dollars. This was not a consumer appliance. Raytheon's marketing division proposed targeting restaurants and railroad dining cars. Commercial kitchens needed speed more than households. They could afford the price. They had the electrical infrastructure. The device could reduce cooking staff and accelerate service. The engineering team spent 1946 refining the design. They added a rotating turntable to ensure even heating. The original prototype created hot and cold spots because microwave energy distributed unevenly inside the cavity. Food near the walls heated faster than food in the center. The rotating platform solved this by moving food through different energy zones. They developed the interlock system. The magnetron had to shut off instantly when the door opened. Microwave radiation at 2,450 MHz could cause tissue heating in humans. The eyes were particularly vulnerable. The door seal became a critical safety feature. Engineers tested seal integrity obsessively. Spencer worked on power modulation. The original prototype operated at full power constantly. Binary. On or off. He developed a system to vary the magnetron output, allowing different cooking intensities. Low power for defrosting. Medium for reheating. High for rapid cooking. The device received its commercial name in March 1946. The Radarange. The name connected the technology to its radar origins while suggesting its cooking function. Marketing considered this important. The technology was strange. The physics was invisible. Consumers needed to understand the military pedigree. Raytheon built the first commercial unit in 1947. Installation went into a Boston restaurant. The owner was skeptical but intrigued. His kitchen operated at capacity during lunch rush. Traditional ovens couldn't handle the volume. The Radarange promised to cook a hamburger in 90 seconds. The test ran for 3 months. Line cooks learned the technology gradually. They discovered that microwave cooking required different timing than conventional heat. A potato baked in 60 minutes in a regular oven cooked in 4 minutes in the Radarange. But the texture was different. Drier. The skin didn't crisp. Certain foods worked perfectly. Reheating. Defrosting. Cooking vegetables. Other applications failed. Baking bread. Roasting meat with browning. Creating crispy surfaces. Microwaves excited water molecules but didn't generate the Maillard reaction that created browning and complex flavors. The restaurant owner bought the unit. The investment was substantial, but the speed advantage justified the cost during peak hours. Raytheon recorded its first sale. By 1949, Raytheon had sold approximately 1,000 commercial radar ranges. Airlines installed them. Hospital kitchens. Railroad dining cars. Cruise ships. Anywhere that speed mattered more than culinary finesse. But consumer adoption remained zero. The units were too large, too expensive, too power-hungry. They required professional installation. Home kitchens couldn't accommodate them. Raytheon's consumer products division, Waltham. Engineers faced a fundamental challenge. The magnetron that made microwave cooking possible was designed for military radar. It was large, power-hungry, and required cooling systems. Shrinking it for home use meant redesigning core components. The military magnetron generated 10 kilowatts of microwave power. Radar needed that intensity to detect aircraft at 50 miles. Cooking food required far less. Engineers calculated that 700 to 1,000 watts would suffice for household cooking. This meant developing a lower power magnetron specifically for appliances. The cooling system presented another obstacle. Military magnetrons used water cooling. Liquid circulated through channels around the tube, absorbing heat. Home appliances couldn't use water cooling. It added weight, complexity, and potential leak points. Engineers needed air cooling, which was less efficient but more practical. Spencer's team began experimenting with smaller cavity designs. They reduced the copper cylinder's diameter from 4 inches to 2.5 inches. They shortened the tube length. They modified the electron path. Each change affected performance. Smaller magnetrons generated less uniform microwave fields. Engineers compensated by adjusting cavity geometry. The power supply required similar reduction. Military radar used heavy transformers that stepped voltage up to levels necessary for high-power transmission. Cooking magnetrons needed simpler, lighter power supplies. Engineers developed compact transformers using thinner wire and different core materials. By 1954, Raytheon had prototype magnetrons weighing 12 pounds instead of 40 pounds. Power consumption dropped to 1,500 watts. The tubes operated reliably for 2,000 hours before failure. This was marginal for consumer products but represented significant progress. Japanese manufacturers entered the picture in 1955. Toshiba licensed Raytheon's patents and began developing their own microwave ovens. Japanese engineers brought different priorities. American designs emphasized power and speed. Japanese designs emphasized miniaturization and efficiency. Toshiba reduced the magnetron further. They achieved 1,000 watt output in an 8-pound package. They used innovative ceramic insulators that withstood heat better than American materials. They developed more efficient transformers. By 1959, Toshiba had built a countertop microwave oven weighing 55 pounds. American manufacturers noticed. If Japanese companies could miniaturize the technology, Raytheon needed to accelerate development or lose market position. The breakthrough came in 1965. Engineers at Amana, now owned by Raytheon, built the first practical countertop microwave for home use. The Amana radar range measured 22 by 18 by 14 inches. It weighed 45 pounds. Power consumption was 1,300 watts from a standard 120-volt outlet. Price was $495, equivalent to roughly $4,700 in 2025 dollars. Still expensive, but no longer impossible. The unit used a magnetron producing 800 watts of microwave power at 2,450 MHz. The cavity measured 1.2 cubic feet. A mechanical timer controlled cooking duration. A simple mechanical interlock stopped the magnetron when the door opened. No digital controls. No programming. Just power and time. Amana manufactured 10,000 units in 1967. They sold through appliance stores and department stores. Marketing emphasized speed and convenience. A baked potato in 4 minutes. Coffee reheated in 30 seconds. Frozen dinners ready in 6 minutes. Consumer response was cautious. The technology seemed unnatural. Invisible energy cooking food. No flames. No hot coils. Just a humming sound and heat appearing inside the food. Early adopters were professionals with money and curiosity. Doctors. Engineers. Business executives. People comfortable with new technology. Sales grew slowly. By 1970, roughly 40,000 microwave ovens operated in American homes. This represented less than 0.1% of households. The appliance remained a novelty, not a necessity. Consumer Reports Testing Laboratory, Mount Vernon, New York. Technicians measured microwave leakage from 17 different oven models. The results troubled them. Every unit leaked some radiation. Amounts varied. Some leaked minimally. Others exceeded recommended exposure limits at close range. The measurements used the same standards developed for military radar operators. The threshold was 10 milliwatts per square centimeter at 2 inches from the surface. Most ovens tested below this level. But several exceeded it near the door seal. 2 units leaked dangerous amounts when the door alignment was slightly off. Consumer Reports published the findings in their June 1968 issue. The article didn't condemn microwave ovens outright. But it raised serious questions about safety standards and quality control. The public reaction was immediate. Sales dropped 40% in the following quarter. Raytheon and Amana responded with engineering improvements. They reinforced door seals. They added redundant interlock systems. They implemented quality control testing that measured leakage on every unit before shipment. But public concern persisted. The question was biological. What did microwave radiation do to human tissue? Military radar operators had shown some health effects after prolonged exposure. Cataracts. Tissue heating. But these cases involved high-power radar systems. Cooking ovens generated far less power. The exposure was intermittent. The door shielded users. Research in the late 1960s provided some answers. Microwave radiation at 2,450 MHz was non-ionizing. It couldn't break chemical bonds or damage DNA like X-rays or gamma radiation. The primary biological effect was heating. Water molecules absorbed the energy and generated heat through friction. This was the same mechanism that cooked food. The critical factor was intensity and duration. Brief exposure to low-level microwave radiation caused no measurable biological harm. Prolonged exposure to high-intensity radiation caused tissue heating. The eyes were most vulnerable because they lacked blood circulation to dissipate heat. Studies of microwave oven users showed no elevated health risks. The exposure levels were too low. The door seals worked. The interlock systems functioned. But perception lagged behind evidence. In 1971, the FDA established federal safety standards for microwave ovens. Maximum leakage of 5 milliwatts per square centimeter at purchase and 1 milliwatt per square centimeter throughout the oven's lifetime. Manufacturers had to certify compliance. Units exceeding these levels couldn't be sold. The regulations restored some consumer confidence. Sales recovered gradually. By 1975, roughly 1 million American households owned microwave ovens. This represented about 1.5% penetration. The technology was proven safe but still not mainstream. Price remained a barrier. The cheapest models cost $300, equivalent to about $1,700 in 2025 dollars. Most families couldn't justify that expense for a convenience appliance. Conventional ovens worked fine. They were familiar. They produced better-tasting food for many applications. The turning point came from unexpected competition. Japanese manufacturers flooded the American market with lower-priced models. Sharp, Sanyo, and Panasonic built microwave ovens in high-volume factories. They achieved economies of scale that American manufacturers couldn't match. By 1979, Japanese imports cost $200 to $250. American manufacturers responded by moving production offshore or partnering with Asian companies. Amana contracted with Samsung. General Electric partnered with Toshiba. The price competition drove costs down rapidly. By 1980, basic microwave oven sold for $150. This represented roughly $550 in 2025 dollars. Still significant but within reach of middle-class families. The value proposition shifted. At $500, a microwave was a luxury. At $150, it was a justifiable convenience. American kitchens. The microwave oven crossed the threshold from novelty to necessity. Market penetration reached 60% of households. 10 years earlier, it had been 1.5%. The transformation happened faster than any previous kitchen appliance. Faster than dishwashers. Faster than electric mixers. Faster than garbage disposals. The shift came from multiple factors converging. Price dropped below $100 for basic models. Working women increased from 43% of the workforce in 1970 to 54% by 1985. Single-person households grew as marriage rates declined and divorce rates increased. All of these groups valued speed over culinary tradition. The frozen food industry adapted specifically to microwave technology. Stouffer's, Swanson, and new companies like Lean Cuisine designed meals that cooked properly in microwave ovens. The packaging mattered as much as the food. Engineers developed containers that withstood microwave heating without melting or releasing chemicals. Some materials even included metallic elements that browned food through Susceptor technology. Susceptors were thin metallic films laminated inside cardboard. When microwaves hit the metal, it generated intense surface heat. This allowed pizzas to get crispy crusts and sandwiches to toast. The innovation solved one of the microwave's persistent limitations. It couldn't brown food. Susceptors provided localized conventional heating within the microwave environment. Food companies invested heavily in microwave-specific product development. By 1986, frozen food sales directly attributed to microwave cooking exceeded $2 billion annually. The appliance drove food industry innovation in ways Percy Spencer never imagined. His melted chocolate bar in 1945 had created an entire market segment 40 years later. The engineering continued evolving. Manufacturers added carousel turntables as standard features. They integrated digital controls replacing mechanical timers. They developed sensor cooking that detected humidity released by food and adjusted time automatically. High-end models incorporated convection heating elements, creating combination ovens that microwaved and browned simultaneously. Power levels standardized at 700 to 1,100 watts for home units. Cavity sizes settled around 1.0 to 1.5 cubic feet. These dimensions fit standard counter depths and provided enough space for dinner plates and casserole dishes. Larger models served families. Smaller models fit apartments and dorm rooms. The microwave entered popular culture as a symbol of modern life. Television shows featured characters heating TV dinners in seconds. Comedians joked about Americans forgetting how to cook real food. Social critics worried about family meals disappearing. The microwave represented technology replacing tradition, convenience superseding craft. But adoption data showed something more nuanced. Families didn't stop cooking entirely. They used microwaves for specific tasks. Reheating leftovers. Defrosting meat. Cooking vegetables. Making popcorn. The conventional oven remained essential for roasts, baked goods, and dishes requiring browning. The microwave supplemented rather than replaced. College students became heavy adopters. Dorm rooms prohibited hot plates but allowed microwaves. An entire generation learned to cook using microwave-only recipes. Cup noodles. Instant oatmeal. Microwave mac and cheese. These products were engineered around the technology's limitations and capabilities. By 1990, market penetration reached 78% of American households. The microwave had become as common as the refrigerator. New homes included dedicated counter space or cabinet cavities for microwave installation. Rental apartments advertised microwave-equipped kitchens as amenities. The global market exploded. Japanese households embraced microwaves even more enthusiastically than Americans. European adoption lagged but accelerated through the 1990s. South Korea became both a major manufacturer and consumer market. Percy Spencer's accidental discovery had transformed into a worldwide industry worth billions of dollars annually. The principle remained identical. Magnetrons generating 2,450 MHz radiation. Water molecules vibrating. Heat from molecular friction. But the application had expanded beyond anything imagined in 1945. Percy Spencer died at age 76, 25 years after discovering microwave cooking. He lived to see his accident become an industry. Raytheon had awarded him the Distinguished Service Medal. The American Institute of Electrical Engineers recognized his contributions. But he remained largely unknown outside engineering circles. His story captured something fundamental about innovation. The prepared mind recognizing significance in the unexpected. Spencer didn't discover microwave radiation. That physics had been established decades earlier. He didn't invent the magnetron. British engineers developed that for radar. His contribution was simpler and more profound. He noticed something wrong and investigated. The chocolate melted when it shouldn't have. Most people would have dismissed it. Warm factory. Warm pocket. Chocolate melts. Spencer saw an anomaly. He tested it. He experimented systematically. He moved from observation to mechanism to application. This was the scientific method operating in real time on a factory floor. The microwave oven's history reveals how technology moves from military to civilian applications. The magnetron was a weapon technology. It detected enemy aircraft. It won battles. The same physics that found submarines cooked frozen dinners. This pattern repeated throughout the 20th century. GPS Internet. Duct tape. Superglue. Military necessity driving research. Commercial applications following years later. By 2025, roughly 95% of American households own microwave ovens. Global ownership exceeds 1 billion units. The technology has barely changed since the 1980s. Magnetrons still generate 2,450 MHz radiation. Cavities still contain the energy. Turntables still rotate food. Digital controls have replaced mechanical timers. Sensors have improved. But the fundamental principle remains Spencer's discovery from 1945. Modern magnetrons last 2,000 to 5,000 hours before failure. At 30 minutes daily use, that's 11 to 27 years. Most microwaves are replaced for aesthetic or feature reasons before the magnetron fails. The core technology is remarkably reliable. Millions of magnetrons operate daily, descendants of Spencer's radar tubes. The efficiency question persists. Microwave ovens convert roughly 50% of electrical energy into microwave radiation. Conventional electric ovens convert about 12% of electricity into cooking heat. Gas ovens reach roughly 6% efficiency. For heating small quantities quickly, microwaves are the most efficient cooking method. For large roasts or baked goods requiring dry heat, conventional ovens remain necessary. The health concerns from the 1970s have faded. Decades of use produced no epidemic of microwave-related illness. The FDA standards proved adequate. Door seals work reliably. Interlock systems prevent exposure. The radiation is non-ionizing. The primary risk is burns from superheated liquids or containers, not the microwaves themselves. Food quality debates continue. Microwave cooking produces different results than conventional methods. Vegetables retain more nutrients because shorter cooking times cause less breakdown. But texture suffers. Meats don't develop the Maillard browning that creates complex flavors. Baked goods don't achieve proper crust. These limitations are physics, not engineering failures. The Seceptor innovation partially addressed browning, but it's still inferior to oven or pan cooking. Combination microwave convection ovens offer better results but at higher cost and complexity. Most users accept the limitations as trade-offs for speed. Percy Spencer's legacy isn't the microwave oven itself. His legacy is the recognition that accidents, properly investigated, reveal possibilities. The chocolate melted. He could have thrown it away and gotten another. Instead, he asked why. That question launched an industry. The microwave exists because someone noticed something odd and didn't dismiss it. Because someone had spent decades solving technical problems and recognized an anomaly worth investigating. Because preparation meets opportunity in unexpected moments. October 1945. Building 26. Melted chocolate. A revolution started by accident.